All right, AP Chemists, welcome to another lecture. This is Chapter 14, Lecture number 3. Today we will be covering topics in acids and bases, and specifically we'll be talking about the behaviors of basic solutions. So let's go ahead and get started. So to begin our conversation around bases, today we're going to be talking about the behavior of specifically weak bases. The nice thing about calculations involving weak bases is that you already are familiar with how to solve weak acid problems, and as it turns out, bases are going to be a very similar process. One thing you want to be aware of is whereas for a weak acid, you are welcome to either write a hydrolysis reaction, that is to show the acid donating its proton to a water molecule in solution, or again, you can also write those acid equations as straight up dissociations. For most weak bases we'll be dealing with, you're going to be required to write a hydrolysis reaction. And recall from a Bronsted-Lowry definition of acid-base behavior, we'll see the base acting as the proton acceptor. And again, within an aqueous solution, the base, in this case, for our example, ammonia, is going to be accepting a proton from the water molecule. And as it accepts that proton, we end up forming the ammonium ion, NH4 positive, and the hydroxide ion, OH negative. From that point on, once you've written your hydrolysis reaction, the process of solving a weak base problem is going to look the exact same as it does for a weak acid. That is to say, you're going to be setting up an ice table. Rather than using a Ka for an acid, instead you'll be using the Kb for the base. And in general, you'll be calculating the hydroxide ion concentration at equilibrium, meaning in general, the pathway will take you through POH first rather than pH. But beyond that, this is just a simple ice table problem and should not look much different from what you've already done involving weak acids. Something I'd like you to keep in mind as you approach these weak base problems is that the majority of weak bases that the AP test will give you are going to be some derivative of a familiar species, which is ammonia, NH3. Ammonia acts effectively as a base because, again, if you look at its Lewis dot structure, recall that ammonia has a lone pair of electrons, which makes it a great candidate for engaging in Lewis acid-base behaviors, as you saw in the example problem which we just discussed. But keep in mind, anytime you find nitrogen acting in a compound in a similar way, that particular compound will be also likely to show the same sort of behaviors as ammonia does, that is, donating the electron pair to form a coordinate covalent bond, and as such, it's going to be a candidate for acting as a base. Some other common bases that you'll see showing up in the AP test, again, derivatives of ammonia, are things like methylamine, where we're substituting a methyl group, that is a CH3, for one of the hydrogens in the ammonia. You may also come across something like dimethylamine, where instead we're substituting two methyl groups for the hydrogens in the ammonia molecule. And again, you could also see things like ethylamine as well, ethylamine where we'd substitute a ethyl group for one of those hydrogens as well. But note, for all of these different organic molecules, there still is that nitrogen atom that has the lone pair of electrons sitting there just waiting to be used to form a bond, and again acting as an electron pair donor, and therefore exhibiting basic behavior from our Lewis acid-base definitions. Now, a type of problem that you'll often come across in the AP test is where they'll ask you to compare the relative strength of a number of different bases. And just like we saw with comparison of acid strengths, it's going to require us to kind of draw on a variety of different places from our knowledge to make these decisions about which base is going to be the stronger base. Primarily, number one, recall that you have already previously memorized a list of the strong bases which you're likely to encounter. Again, those are the alkali metal hydroxides and then calcium, strontium, and barium hydroxide. But again, if you're comparing the strengths of weak bases, really we're again dependent upon comparisons of the relative Kb values of those bases. And one of the tricks that you got to kind of watch out for the AP test is oftentimes rather than giving you the Kb value for a weak base, they might instead give you a Ka value for the conjugate acid of that weak base. And there's a relationship that exists between the conjugate acid species and the conjugate base species, which we'll discuss on our next slide. But again, for the time being, we're mostly going to focus on our understanding of the relative strengths of the weak bases from their Kbs. Now, recall from our previous conversation that the stronger an acid, the weaker its conjugate base is going to be in a Bronsted-Lowry acid-base interaction. So when we're looking at example number 1 here, we're going to make use of that fact to make some decisions here about which of each of these different species is the stronger base out of the given pairs. So let's go ahead and take a look here at the first of our examples right here, in which we're comparing the basic behavior here of the nitrate ion NO3 negative versus ammonia NH3. Now note here on the data table on the right-hand side, we've given you a Kb value for the weak base ammonia. That Kb value is 1.8 times 10 to the negative fifth. A pretty small Kb as far as these things go again, but recall that any of these weak species is going to have a K value which is significantly smaller than 1. But the thing we're comparing that ammonia to is the nitrate ion NO3 negative. We haven't given you a Kb value for the nitrate ion because, as it turns out, you're already familiar with something that has a relationship to the nitrate ion. That is the species nitric acid. Recall that upon dissociation, nitric acid will split apart to form hydrogen ions in solution and the nitrate ion in solution. And if we look at this from a Bronsted-Lowry perspective, where we're looking at the hydrolysis reaction, note here that the nitrate ion is in fact the conjugate base of the strong acid nitric acid. And understanding the idea that the stronger the acid, the weaker its conjugate base, that's going to tell us here that because nitric acid is a strong acid, the nitrate ion has almost no ability whatsoever to act as a proton acceptor within these aqueous solutions. And as such, the nitrate ion is a very, very weak acid indeed, much weaker, as it turns out, than the weak acid ammonia, which we're comparing here. So our justification here is going to be the nitrate ion is the conjugate base of a strong acid, and thus itself is the weaker of the bases between this pair. Now, comparing our second pair, we're now going to go ahead and look at the species water, H2O, versus ammonia. We already know the ammonia, again, is a weak base who has a Kb value of 1.8 times 10 to the negative fifth. Water, recall from our previous conversations, is an amphoteric species. That is a species that can both act as a proton donor and a proton acceptor. And if we're going to be showing a reaction where water is acting as a proton acceptor within a hydrolysis reaction, that's essentially the autoionization of water, which we're describing right there. And we already know the Kw value for the autoionization of water, that's a value we've seen on a number of occasions before, is 1.0 times 10 to the negative 14th. Implying, therefore, that water is a significantly weaker base than ammonia, given that Kw is significantly smaller than the Kb value for ammonia of 1.8 times 10 to the negative fifth. So taking care of the first two examples here, let's take a look at the next two. We've got the hydroxide ion, OH negative, and ammonia, NH3. And in this instance here, this is a pretty easy one to decide here, because we recall from previous conversations that the hydroxide ion is the strongest base that can exist within an aqueous solution. And again, our justification there was that any base stronger than hydroxide ions within the solution would simply accept protons from waters, and in doing so would form hydroxides in the solution. So again, no matter how strong of a weak base the ammonia is there, the hydroxide ion as the strongest base present in an aqueous solution must therefore be the stronger of the pair. So the hydroxide is going to be the stronger of that pair. The final example we've got here is a comparison between CH3 and H2, that is a methylamine, in comparison to ammonia NH3. And in this instance here, we're going to be entirely dependent upon a comparison of the relative Kb values. Both ammonia and methylamine act as proton acceptors, as we previously discussed there. And you'll notice here that the Kb value for ammonia is smaller than the Kb value for the methylamine given in the table to the right-hand side here. And again, a smaller Kb value indicates a system that more heavily favors the reactant side, implying, therefore, that ammonia is going to be the weaker base of this particular pairing here. So to summarize all the strategies we used here in this particular example problem, the first part, we recognized that the conjugate base of a strong acid is always going to be an incredibly weak base. For our second example there, we saw that water, again, being an amphoteric species, can exhibit basic behavior, but given Kw is a very, very, very small K value of 1 times 10 to the negative 14th, Water in most instances is going to be a weaker base than most species that we're comparing it to. The third example there, the hydroxide ion, again, is the strongest base that can exist within an aqueous solution. And then again, in our fourth example there at the bottom, we're really just comparing the relative sizes of the Kb. The stronger base will be, again, the one with the larger value of Kb. Now, one final thing I'd like to have a look at here before we move on to other topics in acids and bases in our next lectures is a particular relationship that exists between the equilibrium constants Ka and Kb for a weak acid and its respective conjugate base. Have a look here at the equations which we have written on our page here. The first of those equations is the dissociation equation describing the separation of the weak acid HA, splitting apart into the hydrogen ion H positive and its conjugate base anion A negative. From that equation, we could write a Ka expression, which again, as always, is the products over reactants here, the concentration of H positive times the concentration of A negative divided by the concentration of the molecular acid species HA. Now, in the second equation we've written down there, in this instance, we're looking at the basic behavior of the species A negative. That is, again, the conjugate base of the weak acid HA. Because HA is a weak acid, that implies that its conjugate base A negative is itself a relatively strong base. And as such, A negative can accept protons from water. In this reaction, we see A negative picking up the proton from H2O to form HA and OH negative, again acting as a proton acceptor, a base. And from that again, we could write the Kb value of the conjugate base here, which would be concentration of HA times the concentration of OH negative divided by the concentration of A negative. And again, note we're not going to include water within that equation because, again, water, the liquid phase species, exists at relatively constant concentration. Now, something important I'd like you to note here is this. What we're going to go ahead and do is we're going to go ahead and multiply our value of Ka times the value of Kb for the conjugate base of that acid. And note here, as we multiply those K values together, we get H positive times A negative over HA multiplied by HA times OH negative over A negative. And upon multiplying those two equilibrium constants together, you'll notice that we see a whole bunch of things canceling out. That is, in particular, we see the HA in the numerator for the Kb value canceling with the HA in the denominator for our Ka value. And you'll also notice here that the conjugate base anion A negative is in the numerator of our Ka and the denominator of the Kb, so those cancel out as well. And after canceling those values, you'll see here that the remaining things that remain behind after that cancellation simply is the concentration of hydrogen ion times the concentration of hydroxide ion, which we know from previous conversations is our definition of the autoionization constant of water, that is Kw. So for a weak acid and its respective conjugate base, the product of the Ka and Kb of those two species is equal to Kw, that is 1.0 times 10 to the negative 14th. And this is a really useful relationship to understand because if you're given a Ka value of a weak acid, that implies that you can rapidly calculate the Kb value of its conjugate base. And that's something the AP test will often like to do with acid-base problems, is that they will ask you a bunch of problems about, say, a basic species, but they won't give you the Kb value of the base. Instead, somewhere else in the problem, they might give you a Ka value for a species that you will need to recognize as the conjugate acid of that species. So as a quick example, we can kind of imagine thinking about a weak acid like, say, acetic acid, that is vinegar. The Ka value of vinegar is 1.8 times 10 to the negative 5th. And knowing the Ka value of acetic acid, I could also therefore rapidly calculate the Kb value of the conjugate base of acetic acid, that is the acetate ion. And you'll see here as I rearrange the expression Ka times Kb equals Kw to solve for Kb, I will get Kb is equal to Kw over Ka, And plugging in some values there, the Ka of acetic acid there was 1.8 times 10 to the negative fifth. Our Kw for water, the familiar 1.0 times 10 to the negative 14th. And making this division here, you'll note here that I can solve for the Kb for the acetate ion is essentially 5.55 repeating times 10 to the negative 10th, so 5.6 times 10 to the negative 10th, a very small value of Kb. And in particular, what I'd like you to understand about the relationship described by this equation is that it actually provides for us a quantitative basis for something that we already had a fundamental understanding of. That is to say, the stronger an acid, the weaker its conjugate base. So you can imagine here, looking at the equation Ka times Kb equals Kw, recognizing that Kw is a constant of 1.0 times 10 to the 14th, for a species with a larger value of Ka, that implies that it must therefore have a relatively smaller value of Kb for the conjugate base. That is, there's an inverse relationship between those two K values. And again, that kind of explains exactly what we already knew. Stronger acids have weaker conjugate bases and vice versa. So that's about it for special topics in acids and bases, dealing with bases here. And thanks for listening. We'll see you on the next one.